Girls, good morning. How are you all? I hope you followed the last video that I sent you and understood the lesson. And today we will see the continuation of the first video. So, in the previous session, we saw that the wave function of the particle which has the energy E is written as psi of x a sine kx, where k is equal to root of 2me by h cross squared. This and all is found in the last video. If only you understood the last video, you can follow this video. So, when we substitute this k value into this equation 12, we will get psi of x equal to a sine root of, in the place of k we are substituting the expression 2me by h cross squared into x. We know the E stands for the quantized energy, which is equal to En h cross squared pi squared by 2m h L squared into n squared, where this n takes the quantum number value according to the state in which it is existing. So, substituting this En value in this equation in the place of E, we will be getting psi n of x equal to a sine n pi x by L. In this equation, you just substitute E value and simplify, you will be getting psi n of x a sine n pi x by L. The eigenfunction, this is the eigenfunction corresponding to energy eigenvalue En. Now we will find what is the value of A, which is arbitrary. This can be found, the constant value A can be found using the normalization condition. We know the normalization condition is within the limits 0 to any value a, psi n of x the whole squared into dx equal to 1. This is the normalization condition which all of you know. Here we have the two limits, not 0 to a but 0 to L, the boundary between 0 and L, the particle existing between these two boundaries 0 and L. Therefore, in the place of psi n of x, we are substituting a sine n pi x L into dx. It is squared, therefore, a squared within the limits 0 to L sine squared n pi x divided by L into dx equal to 0. You need to integrate this term, integration over sine squared n pi x by L dx. How do you integrate? It is just a simple integration using the formula sine squared theta is equal to integral over sine squared theta is equal to what? It is 1 minus cos 2 theta by 2. So use this formula and integrate over. So you will end up this integration term leading to the value L by 2. So a squared is outside. It will be in the integration term will be equal to a squared L by 2 is equal to 1 because it is normalizing condition. So when we rearrange this a squared, take this 2L, this 2, this side, you will be a squared is equal to 2 by L. So a is equal to root of 2 by L. So we got the normally the constant value for a, which is root 2 by L. So the wave function corresponding to the energy value can be written as psi n of x equal to root 2 by L sine n pi x by L, where n takes the values of 1, 2, 3, etc. This is the probability density curve corresponding to the uh, ground state, first excited state, and 19th excited state. You see, corresponding to if it is a ground state, we have one hump like this, and if it is the first excited state, you will be getting two humps, and if it is the 19th excited state, we will be having around 20 curves like this. This is the probability density distribution curve. In the next session, we are going to see is the particle in a box, how the momentum is quantized. The particle's momentum is being quantized, how? So, in order to find the quantized value of momenta, we will start with finding the average value or the expectation value of momentum of the particle that exists within one dimensional box. So how do you calculate the average value or the expectation value or the most probable value? P bar is equal to within limits, integral limits between minus infinity to infinity, psi star, the operator P psi dx. I hope we have already studied in our classroom. I hope you remember the expression. So now what this P is, this is the operator momentum, and we are to write the wave function psi n, and psi star stands for the complex form. Here, since we do not have any I value, so it is psi star will be equal to psi, which is equal to root of 2 by L sine n pi x by L. So when we differentiate with respect to x, we will be getting this value root of 2L by L n pi L cos n pi x by L. This we will be needing in the next equation. Therefore, I have differentiated this equation here. So in this equation, we are just substituting the value of the operator minus infinity to plus infinity psi star. The operator P is equal to h cross by I d by dx into psi dx. I hope you remember the expression for the momentum operator. So, in our case, the integral term limits between 0 to L, and psi star is equal to root 2 by L psi n pi x by L into the operator, and the psi term is put here. Taking all the constant terms outside the integration, we have written here root of 2 pi L, here integral 2 pi L, therefore it comes out as 2 pi L. Here is the constant h cross by I. So integral over 0 to L, all the other terms are remaining. So when we differentiate this term with respect to x, because there is d by dx in front of this expression, so this expression need to be differentiated with respect to x. When we differentiate, then we are getting cos n pi x by L into n pi by L into dx. So this also is constant term, it is taken out in the next equation, in the next part, and within the integral part we have cos n pi x by L into sin n pi x L into dx. When you see this integration part, you will remember this is in the form of minus infinity to plus infinity integration sin ax cos ax into dx, which is equal to 1 by 2a sin squared ax within the limits. So this equation similars the equation, so we can substitute in this formula in the place of the integration. But only difference, in the place of L we have n pi L here. So take the integration term and substitute the given formula. We are getting the final equation as L by 2n pi into sine squared n pi. Take the integration term and put it back into the equation, and we will be getting the average value of P, and when we simplify it we will be getting h cross by IL sine squared n pi. We know anything into pi, sine of pi is equal to 0. Therefore, sine squared pi also will be equal to 0. Therefore, this term will be equal to 0. Therefore, the expectation value of the particle's momentum is equal to 0. This looks strange to us, is it not? We will check it by another expression. You know, the energy of the particle is given by the p squared by 2m, and p squared is equal to 2me, and p is equal to plus or minus 2me. When we substitute the energy value n squared pi squared h cross squared by 2ml squared and simplify that, we will and take out of the root, we will be getting p is equal to plus or minus n pi h cross by L. This plus or minus denotes the particle is moving back and forth between the two boundaries 0 to L. So, the average value of the momentum can be found by the sum of the momenta of the particle moving back and forth divided by 2. So, plus sign when the particle is moving back forward, and minus sign when the particle is moving backward, divided by 2, which is leading to 0. Therefore, the average momentum or the expectation value of the momentum is equal to 0. Now, according to this equation 5, there must be two momentum eigenfunction for every function, energy eigenfunction corresponding to the two possible direction of motion. So, we will find the eigenvalues of the quantum mechanics operator P, momentum operator P. So, we will see how to find the eigenvalue equation of the momentum. That can be found using this expression operator P psi n is equal to normal P psi n, where Pn is the real number and psi n is the eigenfunction. It should be eigenfunction of the momentum operator. We will see whether the eigen energy function or wave function is the momentum eigenfunction also. But we will be noting that the energy eigenfunction is not the momentum eigenfunction using the following expression. According to our expression, it should be equal to operator P psi I is equal to P psi I h cross, just substitute the value of the operator and psi n, and when you simplify you will end up in this expression, and it is not equal to Pn psi n. If it is supposed to be Pn psi n, in the place of cos n pi x we should have sin n pi x. Since it is going as cos n pi x, it is not equal to Pn psi n x. So we need to find what is the correct momentum eigenfunction. For that we are considering this formula, and the later part you will be able to follow by yourself. Just follow the derivation using this formula, and we have written psi n plus psi n minus, and use this equation in this expression and find, we will be getting operator P psi n is equal to normal P psi n. So similarly, psi n minus also will yield the momentum eigenfunction. Thus we conclude Psi n plus and psi n minus are indeed the momentum